Welcome to Monday Part 2. So now we're going to talk about a special kind of wave. The most common example actually is the string on a musical instrument. And this is hard to see in real life, but if you were to visualize the string of a guitar or even a piano or something like that as it is vibrating and making a sound, it might look something like this. So let me explain what I've got here. The darker curve right here, so this one that I'm tracing out here, is what's called, I'm going to call that the forward part of the wave. So this is the string going, up and down or vibrating between its two anchor points. There is a hypothetical thing called a reflected wave that basically is, if you envision this wave going, that it keeps going forward in space. I'm going to follow the line here. Well, that imaginary motion is actually reflected back the other way once it hits this anchor point right here. And that's what this dashed version of it is. Now, we talked about, so think about what does it need for this vibration to be sustained. And for sustained in the course of like a musical instrument, we're talking about a couple of seconds. So if you pluck a guitar string or hit a piano note, you hear that tone for a few seconds until it kind of dampens down, you can't hear it anymore. The string is actually vibrating much faster than that. So what needs to happen for that string to keep vibrating for several seconds for you to hear the tone that long? And it turns out that these nodes, so we talked about nodes in the previous video, have to always be the node for the forward waves and for the reflected waves have to be in exactly the same spot. If that doesn't occur, what happens is something, if this is the case right here where the nodes don't line up, then what happens is one wave sort of cancels out the other. This is called destructive interference. And if this criteria isn't met, the string stops vibrating almost instantly. There's like no motion whatsoever. So cases like the good one here that we want is something called the standing wave. And it turns out that electrons, when they are in atoms, act as if they are a standing wave. And there are some criteria, and that actually constricts or places some pretty big limitations on their behavior. So they can move around like this, but they can't move around or they can't exist in this kind of layout because they would cancel themselves out. There's no electrons, no matter, and that would be bad. Now, I highly recommend that I couldn't embed this, or it didn't make sense to. So don't do that. It didn't make sense to embed this. I'll put an external link to it. But look at this video, and this has a an actual live motion demonstration of standing waves to look at. And look at that. I apologize for the wardrobe choices, but this is still one of the best videos as far as to visualizing the criteria for standing waves. So do that and then come back and we will proceed. Okay, so now I'm going to show you a much more boring still picture version of the video to point out a couple of things. So again, here's our cartoon model of our string vibrating here. A couple things to note. So first off, each time that we added a node, so in the video, the guy kept on changing the frequency that the string was vibrating at, and it would start off looking like this, up the frequency, and it stops moving at all and you keep increasing the frequency until you get this particular frequency, and then you got motion again. You increase the frequency a little more, and then you got no motion until you got this exact frequency, and then it started to vibrate again. And he went on to do a few more. Now, to add a node, like to go from none to 1 to 2, you need to actually add exactly 1/2 of a wavelength. So this cycle right here, this vibration, consists of 1/2 of a complete cycle. This one here is 1 complete cycle. This one here is 1.5 cycles, and so on and so forth. Now, for this to work out, a couple of criteria have to be met. That the area or the length over which the string is vibrating has to be exactly an integer number of half wavelengths. In this case, it is 1/1/2 a wavelength. This is 2/2 of a wavelength, and this is 3/2 of a wavelength. Now, describing this in English can get a little bit ugly, and maybe this is something that can be described in terms of math. So in between now and when I get the next slide up, I want you to think about, is there some mathematical function that could describe this motion? So it kind of starts in the middle, goes up, goes down, goes back up, goes back down again. So is there a function that you know or recognize that has that property? All right, hopefully you came up with one of two answers. One of the trigonometric functions, namely a sine or cosine function, because if you know one function that goes up and goes down and goes back up, it's probably those two. Now, it turns out that the sine function is actually what we want to use. Why is that? It's a little more convenient because at the beginning, this is sort of at position xy, it's sort of at amplitude 0. And sine function has the property of being 0 at x equals 0, so it's just more convenient to use sine than cosine. And so I'm going to define this overall length of the string as capital L. And the way that I would actually describe that first, what's labeled here in the picture as the fundamental vibration, that was just equal to y equals sine pi times x over L. And what the pi over L factor is going to do is guarantee that it's going to be 0 at the very end. At x equals L, this will be 0. Now the second function that's labeled as the first overtone, or n equals 2, has a property calling y equals sine of 2 times pi times x over L. And this factor of 2 in here will make sure that you get 2 half wavelengths or a full wavelength. And last but not least, I'm sure you can maybe guess what's coming here, that the actual function to describe the second overtone, or the n equals 3 vibration, is simply y equals sine 3 times pi times x over L. Now, scientists are lazy. You will note that all of these are quite similar. And could you be a little more, could you condense these into one expression? And the answer is, sure you could. You could just say y equals sine of n pi x over L, where n is actually this number right here. So it's 1 for the fundamental, it's 2 for the first overtone, 3, and they would just keep adding up. You would keep adding 1 to it to get the next vibrational motions out of there. So in this context, n would be an integer from 1 all the way up to infinity, although probably at the infinity level of energy, you'd probably bust the string, but we won't worry about that. And what's important is that n, in this case, is an example in our first instance of something that is called a quantum number. It is a value that usually is not infinitely variable. That namely, that the idea is that in this particular case, n has to be an integer from 1 all the way up. It can't be a negative number, and it has to be an integer. And these quantum numbers give final form to a generic function. So this right here, y equals sine of n times pi times x over L, is an example of something we called a wave function. And it is just like what it sounds like. It is a function that describes a wave. In this case, a fairly straightforward one. Now, as I said, a lot. Scientists are lazy. And once you know that all of these are described by, sine n pi x over L, if you know the generic form of this function, if you just wanted to refer to a particular vibration, you wouldn't even need to mention the entire function at all. Once this is in the back of the head, you could just say the n equals 1 vibration, the n equals 2 vibration, the n equals 3 vibration. And that would actually tell you pretty much almost everything you would need to know. And you wouldn't have to explicitly say this all the time. Now, these quantum numbers actually can tell us a lot of information without us having to do the actual math. So for example, in this context, our vibrating string. All right, so these are already. The quantum number tells us a couple of things. As we alluded to before, it tells us the exact number of half wavelengths. It can also tell you the number of nodes. In this case, the number of nodes is equal to 1 minus the particular quantum number, but again, they're related. And they also tell you the energy of the vibration. These vibrations are increasingly energetic. So this is the least energetic, this is in the middle, and this is the most energetic. So it might not tell you the exact energy of the vibration, but it can give you a relative ranking. Now, this is the simplest type of vibration. And so I'm going to show you one more complicated, or a slightly more complicated thing, and that is drums. So again, in your spare time, Google stop motion photography of drums, and you'll find that the motions that the drum skin attains once it gets hit is actually pretty complicated. And so it is much more complicated than just a simple sine function. And it turns out that those functions require not one, but 2 quantum numbers. And it turns out that there's different kinds of motion in here. So we often rank these motions by nodes. And in the case of a 2-dimensional circular thing, like our drum skin here, there's 2 kinds of nodes. There is a node that is a circle, where the motion is 0, or that they are lines. So there is a line across this that is a circle. So what I want you to do here is, and these numbers right here, this 01, 12, 23, these are the values for the 2 quantum numbers. So what I want you to do is tell you which quantum number is related to the circle nodes and which quantum number is related to the line nodes. So, hit pause, think about it for a second. All right, so the way to look at this is look at, when the number changes and when it doesn't. So across the first column here, you find that there are no line nodes. The motion in these is completely circular. Now, given that going across this first row, the first digit is always 0, that might tell you that the second one is probably dealing with the circle nodes. So this one actually has no circle nodes. This one has 1. It's about right here. I'm trying to trace it out. And this one has 2 circle nodes. The first one is about right here. Kind of see go up and down, up and down. And the second one is about right here. The endpoint doesn't actually count as a node. All right. Now, these guys here exhibit 1 line node. You can kind of see it going across here. And that motion is in concert with or superimposed on the circle node motion too. Here, you've actually got 2 line nodes. One of them is kind of going across like this, and the other one is going across like this. So this is fairly complicated motion, and you can imagine that the actual function is pretty complicated too, which is why we're not actually going to see that. All right, more on these quantum numbers and how they relate to electrons in the next video. See you then.